The story of the universe begins with a singular moment in time, the Big Bang. It's difficult to imagine that the vast, ever-expanding universe we see today began from a point smaller than a single atom, a space so hot and dense that the very laws of physics were pushed to their limits. Around 13.8 billion years ago, this tiny point filled with an unimaginable amount of energy began to expand at an astonishing rate. This expansion wasn't like a typical explosion. It wasn't matter being flung out into empty space. Instead, the Big Bang was an expansion of space itself, setting the stage for the universe as we know it. For the first few moments after the Big Bang, the universe was filled with a dense, hot, and energetic plasma, with particles like protons, neutrons, and electrons moving at incredible speeds. The temperature was so high that these particles couldn't yet combine into atoms. It was a chaotic, energetic environment where space itself was stretching faster than anything could keep up. As time passed, the universe continued to expand and cool. The energy that filled the universe began to transform, and the first fundamental particles of matter began to take shape. These particles formed the building blocks of everything we see today: galaxies, stars, planets, and life. Chapter 2. The early moments of the Big Bang. In the moments following the Big Bang, the universe was a place of extreme conditions. The temperature was millions of degrees, and the universe was filled with a mix of radiation and particles. But as the universe continued to expand, it cooled down rapidly. This cooling allowed the first subatomic particles, protons, neutrons, and electrons, to form. These particles, which are the building blocks of atoms, would eventually combine to create the first atoms. In the earliest stages of the universe, however, these particles existed in a hot, dense state, constantly interacting in ways that we can't yet fully understand. As the universe cooled, the strong nuclear force and electromagnetic force began to dominate. The strong force allowed protons and neutrons to stick together to form the nuclei of the simplest elements, hydrogen and helium. These were the first elements that formed in the universe, and they would go on to become the building blocks of stars and galaxies. At this stage, the universe was still dark and chaotic, but the forces of nature were beginning to take shape. Light itself couldn't travel freely yet, as the universe was still filled with a dense fog of particles that scattered light. It would take hundreds of thousands of years before the universe cooled enough for light to travel freely. Chapter 3. The Cosmic Microwave Background. About 380,000 years after the Big Bang, something significant happened. Atoms began to form. As the universe cooled enough for electrons to combine with protons, neutral hydrogen atoms formed for the first time. This process is called recombination. When this happened, light was finally able to travel freely through space for the first time, no longer scattered by free electrons. The cosmic microwave background, CMB, is the faint glow of radiation left over from this period. This radiation is like a snapshot of the universe when it was just 380,000 years old. It provides us with a direct look at the early universe, and scientists have studied the CMB to learn about the conditions of the universe shortly after the Big Bang. The CMB is a crucial piece of evidence that supports the Big Bang theory. It's a relic of the first light that ever traveled through space and serves as a cosmic fingerprint, telling us about the universe's origins. The light we see from the CMB today is stretched to longer wavelengths due to the expansion of space, and it is this light that provides one of the clearest windows into the universe's early history. Chapter 4. The Birth of Stars and Galaxies. As the universe continued to expand and cool, gas clouds of hydrogen and helium began to form. These clouds were pulled together by gravity, eventually becoming dense enough to ignite the first stars. This process, called stellar formation, took hundreds of millions of years, but it marked a turning point in the evolution of the universe. The first stars, known as population 3 stars, were incredibly massive and hot. These stars were much larger than the ones we see today and burned through their fuel rapidly. Despite their size, they didn't last long. These stars lived for just a few million years before they exhausted their nuclear fuel and exploded in supernovae. These supernovae were some of the most powerful events in the universe, spreading heavy elements like carbon, oxygen, and iron into the surrounding space. These elements would go on to play a crucial role in the formation of planets and, eventually, life. The remnants of these explosions also formed the seeds for the formation of new stars and galaxies. Chapter 5. The formation of galaxies. As more and more stars formed, gravity continued to pull matter together, and the first galaxies began to form. A galaxy is a massive collection of stars, gas, dust, and dark matter bound together by gravity. The first galaxies were relatively small and irregular, often composed of just a few hundred stars. But over time, these galaxies began to merge and grow, eventually becoming the massive, well-structured galaxies we see today, like the Milky Way. The early galaxies were filled with young, hot stars, and many of them were actively forming new stars. The interactions between galaxies, such as collisions and mergers, also played a key role in shaping the structure of the universe. These galactic mergers led to the creation of larger galaxies, including our own Milky Way, and set the stage for the complex structure of the universe. Chapter 6. The Role of Dark Matter. One of the greatest mysteries in the universe is dark matter, an invisible substance that makes up about 27% of the universe's mass. Although dark matter cannot be directly observed, scientists have inferred its existence by studying its gravitational effects on visible matter, such as stars and galaxies. Dark matter plays a crucial role in the formation of galaxies and galaxy clusters. Without it, galaxies wouldn't have enough mass to hold themselves together. Dark matter acts as a sort of cosmic glue, providing the gravitational pull that keeps galaxies intact despite their rapid rotation. In fact, dark matter is thought to make up the vast majority of the mass in the universe, although we still don't fully understand what it is. Chapter 7. The Expansion of the Universe. As galaxies formed and stars were born, the universe continued to expand. The discovery that the universe is expanding was made by Edwin Hubble in the 1920s, when he observed that galaxies were moving away from us in all directions. This discovery led to the formulation of Hubble's law, which states that the farther away a galaxy is, the faster it is moving away from us. This expansion is a direct result of the Big Bang, and it continues today. The universe is expanding at an accelerating rate, and this expansion is driven by dark energy, a mysterious force that makes up about 68% of the universe. Dark energy is causing galaxies to move farther apart, accelerating the universe's expansion and setting the stage for the eventual fate of the cosmos. Chapter 8. The Future of the Universe. So what does the future hold for the universe? Based on current observations, it appears that the universe will continue to expand indefinitely. This expansion is driven by dark energy, which is pushing galaxies farther and farther apart. Over billions of years, the universe will become colder, darker, and more isolated as stars burn out, galaxies move apart, and the remaining energy in the cosmos spreads out across vast distances. One possible outcome is the Big Freeze, in which the universe becomes so cold and spread out that life as we know it cannot survive. However, the future of the universe is still uncertain, and it will depend on the behavior of dark energy, dark matter, and other cosmic forces. After the Big Bang, the universe was a hot and chaotic place, filled with energy, radiation, and subatomic particles. But this intense heat and energy couldn't last forever. As the universe expanded, it began to cool, allowing for the first steps toward the formation of matter. In the early universe, everything was dominated by energy. But as time passed, this energy began to convert into matter, following a process dictated by the laws of physics. The birth of matter was a gradual process, beginning with the formation of the most basic particles that make up everything in the universe. Let's take a look at how the universe transitioned from a boiling, energetic soup into the cosmos we recognize today. The formation of subatomic particles. In the moments after the Big Bang, the universe was so hot that the particles we recognize today, Protons, neutrons, and electrons didn't exist in their usual forms. Instead, the universe was filled with a quark-gluon plasma, a dense, energetic environment where quarks and gluons, the building blocks of protons and neutrons, moved freely, unbound by the strong nuclear force. The temperature was incredibly high, and the particles couldn't combine into stable structures. As the universe continued to expand, it began to cool down, allowing these quarks and gluons to come together. Around 3 minutes after the Big Bang, the temperature had dropped enough for quarks to combine and form protons and neutrons, the particles that make up the nuclei of atoms. The first atomic nuclei. After the first protons and neutrons formed, they didn't remain isolated for long. These subatomic particles began to collide with one another, and as the universe cooled, they began to combine, forming the first atomic nuclei. This process is known as Big Bang nucleosynthesis, and it happened in the first few minutes after the Big Bang. During this period, the universe created hydrogen, helium, and a small amount of lithium. These were the first elements in the universe, and they are still present in the cosmos today. However, heavier elements like carbon, oxygen, and iron didn't exist yet. They would only form much later, inside stars during the later stages of the universe's evolution. The universe's first atomic nuclei were incredibly simple, mostly hydrogen and helium, with a tiny fraction of heavier elements. For about 380,000 years, the universe remained a hot, dense soup of atomic nuclei, free electrons and radiation, and light couldn't travel freely through space due to constant scattering by free electrons. Recombination, the birth of neutral atoms. As the universe continued to expand and cool, the temperature eventually dropped low enough, around 3000 K, for electrons to combine with the atomic nuclei that had already formed. This process, called recombination, allowed the first neutral atoms, mostly hydrogen and helium, to form. The formation of neutral atoms had profound consequences. For the first time, the universe became transparent to light. Before this, photons, light particles, had been constantly scattered by the free electrons in the plasma, preventing light from traveling freely. But once atoms formed, light was able to travel through space without scattering, and the universe was bathed in the first light we can detect today, cosmic microwave background radiation, CMB. The CMB is one of the most important pieces of evidence for the Big Bang theory. It's the faint afterglow of the Big Bang, still detectable across the universe. The CMB provides a snapshot of the universe when it was just 380,000 years old, giving us a glimpse into the conditions of the early universe. The formation of the first stars. After recombination, the universe entered what is known as the Dark Ages, BERT, period when there were no stars or galaxies. The universe was still mostly filled with hydrogen and helium, and there was no visible light. However, gravity continued its work, pulling gas clouds together to form the first protostars. These protostars were the first objects to begin the process of nuclear fusion, the process that powers stars. The first stars, called population 3 stars, were vastly different from the stars we see today. They were much larger, hotter, and more massive, and they burned through their fuel much faster than the stars we're familiar with. These stars played a critical role in the universe's evolution, as they were responsible for the creation of heavier elements like carbon, oxygen, and iron. The fusion reactions inside these stars created energy, which caused them to shine brightly. But after only a few million years, these massive stars exploded in massive supernovae, scattering the elements they created into space. These explosions helped seed the next generations of stars and galaxies, and they set the stage for the formation of more complex structures in the universe. The formation of the first galaxies. As these first stars formed and died, the universe began to take shape in more complex ways. The process of star formation continued to unfold, and over time, gravity caused gas clouds to condense and form the first galaxies. Galaxies are large collections of stars, gas, dust, and dark matter bound together by gravity. The earliest galaxies were small and irregular, often composed of just a few hundred stars. But over time, These galaxies began to merge and grow, eventually leading to the larger, more complex galaxies we see today. The birth of these first galaxies marked a crucial turning point in the history of the universe, as it paved the way for the creation of solar systems, including our own. The role of dark matter in galaxy formation. As galaxies began to form, dark matter played a key role in shaping their structure. Dark matter is an invisible substance that makes up about 27% of the universe's mass, yet it doesn't interact with light or other forms of electromagnetic radiation. Despite its invisibility, dark matter's presence can be inferred by its gravitational effects on visible matter. Dark matter is thought to have helped galaxies form by providing the gravitational pull that allowed gas and dust to collapse and form stars. Without dark matter, galaxies would have had a much harder time forming, as gravity would not have been strong enough to pull material together to form the large structures we see today. This invisible substance was the scaffolding that allowed galaxies to form in the early universe. The evolution of galaxies. As the first stars and galaxies formed, the universe began to take on the structure we recognize today. Over billions of years, galaxies merged, grew, and evolved. Some galaxies became spiral-shaped, while others became elliptical. The interactions between galaxies and the gravitational pull of dark matter continued to shape the universe. Eventually, our own Milky Way galaxy formed, containing hundreds of billions of stars, including our own Sun. The creation of the Milky Way, along with billions of other galaxies, marked the beginning of a new era in the universe, one where complex structures like planets, solar systems, and life would eventually emerge. Chapter Summary. From the initial explosion of the Big Bang to the formation of the first elements, stars, and galaxies, the early universe was a dynamic and rapidly evolving place. It was a time of constant change, driven by the forces of gravity, radiation, and dark matter. The seeds of the universe's structure, stars, galaxies, and the elements necessary for life, were planted in these early stages, setting the stage for the complex, interconnected cosmos we inhabit today. As the universe continued to evolve, it gradually shifted from a dark, chaotic void into a dynamic and organized cosmos. The formation of stars and galaxies was the next great step in the universe's journey. Stars, the engines of light and energy, began to emerge from the cosmic clouds of gas and dust, and galaxies started to take shape. These early stars would not only light up the universe, but also create the heavier elements that would go on to form planets, moons, and even life itself. The formation of the first stars. The early universe was still a hot and mostly opaque place with little structure. However, gravity, the invisible force that governs the motion of objects in the universe, began to pull the first particles of hydrogen and helium together. These atoms formed dense clouds, which, over millions of years, continued to collapse under their own gravity. As the gas in these clouds contracted, it heated up, eventually reaching temperatures high enough to initiate nuclear fusion, the process that powers stars. The first stars, known as population 3 stars, were vastly different from the stars we see today. They were likely enormous, hundreds of times more massive than the Sun, and much hotter. These stars were composed almost entirely of hydrogen and helium, as heavier elements had not yet been created. These massive stars burned through their fuel at an astonishing rate, leading to relatively short lifespans of just a few million years. Despite their brief lives, they played a crucial role in shaping the universe. When these first stars exploded as supernovae, they released vast amounts of energy and scattered heavy elements such as carbon, oxygen, and iron into the surrounding space. These explosions seeded the universe with the building blocks needed to create the next generation of stars, planets, and even life. These supernovae were the universe's first moments of true creation, as they forged the elements that would eventually make up everything we know. The birth of galaxies. As the first stars began to shine and die, their collective gravitational pull helped to form the first galaxies. Galaxies are vast collections of stars, gas, dust, and dark matter, all bound together by gravity. The first galaxies were relatively small, often irregular in shape, and much less organized than the galaxies we see today. They were often referred to as population 3 galaxies, as they formed in the aftermath of the Big Bang and were composed primarily of the first-generation stars. The early galaxies were critical in shaping the universe. As stars within these galaxies continued to be born and die, the elements they released through supernovae were mixed into the interstellar medium, enriching it with heavier elements. Over time, these elements formed the foundation for new generations of stars, each more chemically enriched than the last. As galaxies began to form, they interacted with each other, often merging in spectacular cosmic events. These galactic collisions and mergers led to the creation of larger, more structured galaxies, including the spiral and elliptical galaxies that dominate the universe today. The Milky Way, our own galaxy, is thought to have formed through such mergers, growing over billions of years into the massive organized structure we see today. The role of dark matter in galaxy formation. While we can't see dark matter directly, we know it plays a crucial role in the formation and structure of galaxies. Dark matter is an invisible substance that makes up about 27% of the universe's total mass. It doesn't interact with light or other forms of electromagnetic radiation, but its gravitational effects are undeniable. In the early universe, dark matter acted as a sort of cosmic scaffold, providing the gravitational pull necessary to help gas clouds collapse and form galaxies. Dark matter is thought to have formed vast dark matter halos around the first galaxies. These halos provided the gravitational support needed for galaxies to come together and evolve. Without dark matter, galaxies would not have had the mass necessary to hold themselves together. It is also believed that dark matter played a key role in the formation of galaxy clusters, vast collections of galaxies bound together by gravity. These clusters, along with the dark matter that surrounds them, are some of the largest structures in the universe. The formation of the Milky Way. The Milky Way, the galaxy that we call home, is one of the most well-known examples of galaxy formation. The formation of the Milky Way began over 13 billion years ago, shortly after the Big Bang. Early on, the Milky Way began as a small, irregular galaxy, but over time it merged with other smaller galaxies, growing in size and complexity. The Milky Way is a spiral galaxy characterized by its flat disk, central bulge, and spiral arms. The disk of the Milky Way is filled with stars, gas, and dust, while the central bulge is home to a supermassive black hole that exerts a strong gravitational pull on everything in the galaxy. The galaxy also has a halo of dark matter that surrounds its disk and bulge, helping to hold the galaxy together. Today, the Milky Way is home to hundreds of billions of stars, including our own Sun. It is just one of billions of galaxies in the observable universe, yet it is the only one we know to harbor life. Over the course of its lifetime, the Milky Way has grown and evolved, and it will continue to do so as it interacts with other galaxies in the future. The formation of other galaxies. While the Milky Way is our home, it is far from unique. There are billions of other galaxies scattered throughout the universe, each with its own unique characteristics. Some are spiral galaxies like the Milky Way, while others are elliptical or irregular galaxies. Spiral galaxies are characterized by their distinct spiral arms, which are regions of intense star formation. These arms are made up of young, hot stars, as well as clouds of gas and dust from which new stars continue to form. The Andromeda Galaxy, the Milky Way's closest large neighbor, is a prime example of a spiral galaxy, and it is on a collision course with the Milky Way, which will result in the formation of a new, larger galaxy in about 4 billion years. Elliptical galaxies, on the other hand, are older and contain mostly older stars with little to no new star formation. These galaxies are shaped like ellipses, and they often contain large, dense central regions. They can range in size from small dwarf elliptical galaxies to massive giants that contain hundreds of billions of stars. Irregular galaxies are less common, and their shapes are more chaotic, with no distinct spiral arms or elliptical form. These galaxies are often the result of galactic mergers or collisions, and their irregular shape reflects the disruption caused by these interactions. The evolution of galaxies. As galaxies evolve, they continue to change. Star formation continues, but over time, galaxies run out of the raw materials needed to form new stars. When this happens, the galaxy begins to die, as it no longer has the fuel to create new stars. However, this process can take billions of years. In some cases, galaxies continue to evolve through mergers and collisions with other galaxies. When two galaxies collide, their gravitational forces can trigger a new burst of star formation as gas clouds are compressed and heated, causing new stars to form. Over time, the two galaxies may merge to form a new, larger galaxy. Supermassive black holes at the centers of galaxies. Almost every large galaxy, including the Milky Way, contains a supermassive black hole at its center. These black holes have masses ranging from millions to billions of times that of our Sun. Supermassive black holes are thought to have formed early in the universe's history and grew over time by consuming gas, dust, and even entire stars. The supermassive black hole in the center of the Milky Way, known as Sagittarius A, is just one example of these massive cosmic objects. While black holes themselves are invisible, they can be detected by their effects on nearby stars and gas. The energy released by matter falling into these black holes can create intense radiation, making them some of the brightest objects in the universe. Supermassive black holes play a crucial role in the evolution of galaxies. Their gravitational influence can affect the motion of stars and gas in their host galaxies, and their energy output can regulate the rate of star formation in the surrounding galaxy. Some theories even suggest that the formation of supermassive black holes may have been the driving force behind the growth of galaxies in the early universe. After billions of years of star formation, galactic mergers, and the spread of heavier elements throughout the universe, the stage was set for the formation of a new solar system, a system that would eventually give birth to Earth, the planet we call home. But how did our Sun and its planets come into existence? What processes led to the formation of our solar system, and what role did the earlier history of the universe play in shaping it? The story of our solar system begins with a cloud of gas and dust, remnants of earlier generations of stars that had exploded and dispersed their material across the cosmos. These remnants, rich in elements like hydrogen, helium, carbon, and oxygen, began to collapse under their own gravity, forming the dense and hot region at the center where the Sun would eventually form. The solar nebula. About 4.6 billion years ago, a vast cloud of gas and dust, known as the solar nebula, began to collapse due to gravity. This cloud was primarily made of hydrogen and helium, the most abundant elements in the universe, but it also contained heavier elements, the products of supernova explosions. These heavier elements were crucial for the formation of rocky planets like Earth and for the creation of life as we know it. As the solar nebula collapsed, it began to rotate, and due to the conservation of angular momentum, the cloud flattened into a disk. The dense region at the center of the disk began to heat up as material was pulled toward it, eventually forming the proto-sun, a hot, young star in the making. The outer parts of the disk, still cool and filled with gas and dust, began the process of forming planets, moons, and other objects that would make up our solar system. The birth of the Sun. As the proto-sun continued to collapse, the temperature and pressure at its core increased. Eventually, these conditions became intense enough for nuclear fusion to begin. This process, in which hydrogen atoms are fused into helium, releases enormous amounts of energy and marks the birth of a true star. The energy from this fusion reaction pushed against the force of gravity, stabilizing the Sun and preventing it from collapsing further. At this point, the Sun had entered the main sequence phase of its life, a phase that would last for billions of years. During this time, the Sun would continue to burn hydrogen into helium, providing the energy that sustains life on Earth and fuels the solar system as a whole. The birth of the Sun marked the beginning of a new era in the solar system's history. The formation of planets. While the Sun was forming at the center of the solar nebula, the outer regions of the disk were filled with gas and dust that would eventually come together to form the planets, moons, asteroids, and other objects in the solar system. The process that led to the formation of these objects is called accretion. In the outer regions of the disk, where temperatures were lower, particles of ice and rock began to stick together, forming larger and larger objects. These objects, called planetesimals, collided and merged, gradually growing into the planets we know today. The material in the inner part of the disk, where temperatures were much higher, could only form rocky planets, while in the outer regions, where temperatures were lower, gas giants and ice giants formed. The inner planets: Mercury, Venus, Earth, and Mars. The inner planets, Mercury, Venus, Earth, and Mars, are small, rocky worlds. The high temperatures in the inner regions of the solar nebula prevented the formation of gas giants, so only dense rocky materials could accumulate. These planets formed through the process of differentiation, where heavier materials, such as metals, sank to the center of the planets, while lighter materials like silicates formed the outer layers. The planet Earth, our home, formed from a mixture of rocky material, metals, and water-rich compounds. Over time, Earth's interior became hot enough to cause volcanic activity, which released gases like carbon dioxide, nitrogen, and water vapor into the atmosphere. This volcanic outgassing played a key role in creating the atmosphere we depend on today. The formation of gas giants and ice giants. In the outer regions of the solar nebula, where temperatures were much colder, gas and ice could condense, forming gas giants like Jupiter and Saturn, and ice giants like Uranus and Neptune. These planets are much larger than the inner rocky planets and are primarily composed of gases like hydrogen and helium, as well as water, ammonia, and methane. The formation of gas giants is believed to have occurred through a process known as core accretion. In this scenario, the outer planets first formed large solid cores, which then began to attract vast amounts of gas from the surrounding nebula. These gas giants have thick atmospheres and a large number of moons, many of which are thought to have formed in the same way as the planets themselves, through the process of accretion. The creation of moons and other objects. While the planets were forming, smaller objects also began to take shape. Some of these objects became moons of the planets, while others remained as asteroids or comets. Many of the moons of the gas giants, such as Io, Europa, Ganymede, and Callisto, all moons of Jupiter, are believed to have formed from the same material as their parent planets. These moons likely accreted from the leftover gas and dust in the protoplanetary disk. In addition to moons, smaller objects like asteroids and comets began to form in the outer reaches of the solar system. These objects are remnants from the early solar system and are thought to be leftover planetesimals that never fully coalesced into planets. One of the most important regions for these small objects is the Kuiper Belt, a region beyond Neptune filled with icy objects, and the Oort cloud, a distant spherical shell of icy objects that marks the outer boundary of the solar system. The early Earth. A violent world. As Earth continued to form, it experienced intense bombardment from leftover planetesimals in the solar system. This period, known as the Late Heavy Bombardment, lasted from about 4.1 billion years ago to 3.8 billion years ago, and involved massive asteroid and comet impacts. These impacts reshaped the surface of the Earth, creating craters and releasing massive amounts of heat. It is believed that some of these impacts may have contributed to the formation of Earth's moon, as a giant impact with a Mars-sized body, known as Theia, is thought to have sent debris into orbit around Earth, which eventually coalesced to form the moon. This giant impact also played a role in Earth's tilt and its relatively stable climate, factors that would eventually make the Earth hospitable to life. The Earth's atmosphere and oceans. After the Earth had formed its basic structure, the next major development was the formation of its atmosphere and oceans. Volcanic outgassing released gases such as water vapor, carbon dioxide, and nitrogen into the early atmosphere, while impacts from comets and asteroids brought additional water to the surface. Over time, the planet cooled enough for water vapor to condense into liquid form, forming the first oceans. These early oceans were essential for the development of life. They provided a stable environment for chemical reactions to occur and allowed for the emergence of simple molecules, which would eventually evolve into life. The role of the sun. Throughout the process of solar system formation, the sun played a critical role in shaping the evolution of the planets and their environments. As the sun continues to burn hydrogen into helium, it produces the light and energy that make life on Earth possible. The sun also acts as the anchor of the solar system, keeping the planets and other objects in orbit through its gravitational pull. The sun's solar wind, a stream of charged particles emitted by the sun, also has an important effect on the planets. It interacts with the planets' magnetic fields and can influence their atmospheres. For example, Earth's magnetic field protects our atmosphere from being stripped away by the solar wind, ensuring that life on Earth can thrive. After the formation of the sun, planets, and moons, and as Earth settled into its own unique environment, the next profound event in the history of the universe began: the emergence of life. From simple molecules to complex organisms, the story of life on Earth is a testament to the extraordinary conditions and events that shaped the planet. But how did life begin on Earth? What were the conditions that allowed the first living organisms to form? The origins of life remain one of the greatest mysteries in science, but we have some clues about how life may have arisen. Let's take a look at the possible steps that led to the formation of life on Earth. The early Earth. A hostile environment. At the time when Earth was forming, the planet was far from the hospitable environment we know today. It was extremely hot, with temperatures that could melt rock. Volcanic activity was rampant, spewing gases like carbon dioxide, nitrogen, and water vapor into the atmosphere. The early Earth was constantly bombarded by asteroids and comets, a period known as the Late Heavy Bombardment, which lasted from about 4.1 to 3.8 billion years ago. Despite these harsh conditions, Earth began to cool, and over time, oceans began to form as water vapor in the atmosphere condensed. The planet's atmosphere began to settle into a more stable form, although it was still toxic to life as we know it today, containing high levels of carbon dioxide and little to no oxygen. The role of water. Water was essential for the emergence of life. The presence of liquid water provided a stable environment for the chemical reactions that are necessary for life. Earth's oceans were the cradle for the earliest forms of life, providing a medium in which the first molecules of life could interact. But the water itself wasn't the only factor. It was the complex chemistry that occurred within these oceans that set the stage for life. One of the key ideas about the origins of life is chemical evolution, the process by which simple molecules gradually combine to form more complex molecules, eventually leading to the formation of life. The idea is that life didn't arise all at once. Rather, it evolved over time from simpler, non-living molecules. Earth's oceans, rich in gases and minerals, provided the ideal environment for these chemical reactions. The Miller-Urey experiment, a step toward understanding life's origins. In 1953, a groundbreaking experiment by Stanley Miller and Harold Urey provided significant insight into the conditions that could lead to the formation of life. The Miller-Urey experiment simulated conditions in Earth's early atmosphere using a mixture of gases like methane, ammonia, and hydrogen, and exposing them to electric sparks to simulate lightning strikes. After a week of reactions, they found that amino acids, organic compounds that are the building blocks of proteins, had formed. This experiment showed that it was possible for simple molecules to spontaneously form complex organic compounds, providing a potential mechanism for the chemical evolution that could have led to the formation of life. The formation of basic organic molecules. Amino acids, which are the building blocks of proteins, are just one example of the many organic molecules that likely formed in Earth's early oceans. Over time, these organic molecules could have come together to form larger, more complex molecules like nucleic acids, such as RNA and DNA, and lipids, which form cell membranes. These molecules, which are the foundation of life, are capable of carrying genetic information and building the machinery of living cells. One critical molecule in this process was RNA. RNA is capable of both storing genetic information and catalyzing chemical reactions, making it an ideal candidate for the first molecule of life. Some scientists believe that RNA world hypothesis, the idea that life began with RNA molecules capable of both storing genetic information and catalyzing reactions, could explain how life emerged from simple organic molecules. The first simple life forms. As these complex organic molecules accumulated, they eventually formed the first self-replicating molecules. These molecules were able to reproduce themselves, creating copies of their genetic material. This ability to replicate and pass on genetic information is a key characteristic of life. The simplest forms of life that emerged were likely prokaryotic cells, which are single-celled organisms that do not have a nucleus. The first prokaryotes were likely similar to modern-day bacteria. These organisms were able to metabolize and harness energy from their environment, allowing them to grow and reproduce. These early life forms didn't need oxygen to survive, as Earth's atmosphere at the time was devoid of oxygen. Instead, they used other methods to generate energy, such as chemosynthesis, where chemical reactions with minerals in the environment could be used to produce energy. The Great Oxygenation Event. As life on Earth evolved, some organisms developed the ability to perform photosynthesis, a process that uses sunlight to convert carbon dioxide and water into glucose, a type of sugar, and oxygen. One of the most important organisms to emerge during this period was cyanobacteria, which are believed to have been among the first photosynthetic organisms. Over millions of years, the activities of these photosynthetic organisms began to change the composition of Earth's atmosphere. They released oxygen as a byproduct of photosynthesis, and this oxygen began to accumulate in the atmosphere. This process, known as the Great Oxygenation Event, occurred around 2.4 billion years ago and marked a turning point in Earth's history. The rise in oxygen levels eventually led to the formation of the ozone layer, which protected the planet from harmful ultraviolet radiation and opened the door for the evolution of more complex life forms. The evolution of eukaryotes. While prokaryotes were dominant for billions of years, around 2 billion years ago, a major leap occurred in the evolution of life. Some prokaryotic cells began to incorporate other prokaryotes into their structures, leading to the formation of eukaryotic cells. Eukaryotic cells are more complex than prokaryotes. They contain specialized structures called organelles, including a nucleus, which contains the cell's genetic material. It is believed that the origin of eukaryotes involved a symbiotic relationship between two prokaryotic cells. One of the cells, which could carry out energy-producing processes, was incorporated into the other cell, forming a mutualistic relationship. Over time, these cells evolved into the diverse forms of eukaryotic life that we see today, including plants, animals, fungi, and protists. The development of multicellular life. The evolution of eukaryotic cells set the stage for the development of multicellular life, organisms made up of many cells that work together to form a more complex organism. The first multicellular organisms were simple, but over time, they evolved into more complex plants, fungi, and animals. The ability to specialize and form different types of cells allowed for the rise of more sophisticated organisms, leading to the evolution of multicellular organisms with specialized tissues, organs, and systems. This evolution eventually gave rise to complex ecosystems where organisms interact with one another and their environment, creating a dynamic and interconnected web of life. The importance of evolution. The emergence of life on Earth was not a single event, but a long and gradual process. Through chemical evolution and natural processes, simple molecules gave rise to more complex structures, eventually leading to the formation of life. Over billions of years, life on Earth has continued to evolve, driven by natural selection, genetic mutation, and environmental pressures. The story of life is one of continuous change and adaptation, with each generation building upon the previous one. The complexity and diversity of life we see today is the result of billions of years of evolution, shaped by the laws of chemistry and the forces of nature that have shaped the cosmos since the Big Bang. One of the most profound discoveries in modern cosmology is that the universe is expanding. This expansion began with the Big Bang and continues today, shaping the cosmos in ways we are just beginning to fully understand. The expansion of the universe is not just a historical event, it's an ongoing process that influences everything from the formation of galaxies to the evolution of cosmic structures and the ultimate fate of the universe. In this chapter, we will explore the nature of the universe's expansion, the forces that drive it, and what it means for the future of the cosmos. The discovery of expansion. Hubble's groundbreaking observation. In the early 20th century, astronomer Edwin Hubble made a groundbreaking discovery that would forever change our understanding of the universe. Hubble observed that galaxies were moving away from us in all directions, and the farther away a galaxy was, the faster it appeared to be receding. This observation led to the formulation of Hubble's law, which states that the velocity of recession of galaxies is directly proportional to their distance from Earth. Hubble's discovery provided the first direct evidence that the universe itself was expanding. Prior to this, many scientists believed that the universe was static, neither growing nor shrinking. But Hubble's observations revealed a universe in motion, a dynamic, evolving cosmos where galaxies are constantly moving apart. Understanding the expansion. Space itself is stretching. The expansion of the universe is often misunderstood as galaxies moving through space like objects drifting apart on the surface of a balloon. However, the reality is far more complex. The expansion of the universe is not galaxies moving through space, but rather space itself stretching. This means that the distances between objects in the universe are increasing as the fabric of space itself expands. Imagine a balloon with dots on its surface. As the balloon inflates, the dots move farther apart. Similarly, as the universe expands, the distances between galaxies increase. Space is stretching, carrying galaxies farther apart from one another. This stretching of space is not limited to galaxies. It affects all objects in the universe. For example, light traveling through space also gets stretched, which is why we observe redshift in the light from distant galaxies. As space stretches, the wavelengths of light emitted by galaxies become longer, shifting toward the red end of the spectrum. The role of dark energy in the accelerating expansion. The discovery of the expanding universe was revolutionary, but there was still a major mystery to solve. If the universe was expanding, shouldn't the force of gravity be slowing it down over time? After all, gravity attracts objects, and galaxies should be drawn back toward one another by their mutual gravitational pull. But observations in the late 1990s revealed something unexpected. The universe's expansion was not slowing down. It was accelerating. This discovery led to the identification of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Dark energy makes up about 68% of the universe's total energy content and is thought to act as a sort of anti-gravity, pushing galaxies apart rather than pulling them together. While dark energy is still not fully understood, its effects on the universe's expansion are undeniable. It has become the dominant force in the universe, causing the expansion to accelerate as space itself stretches ever more rapidly. Cosmic inflation, a rapid expansion in the early universe. To understand the expansion of the universe more fully, we need to look back to the first moments after the Big Bang. During the first fraction of a second, the universe underwent a process called cosmic inflation. Inflation was a brief yet incredibly rapid expansion of the universe, in which it expanded exponentially faster than the speed of light. Cosmic inflation is thought to have occurred in the first 10^36 to 10^32 seconds after the Big Bang, during which the universe expanded by a factor of at least 10^26 times in size. This rapid expansion solved many of the puzzles of the early universe, including the horizon problem, the fact that distant regions of the universe appear to have the same temperature, even though they couldn't have been in contact with each other due to the speed of light limit, and the flatness problem, the fact that the universe appears to be very close to geometrically flat. Inflation caused the universe to become uniform on large scales, setting the stage for the slower expansion we observe today. After inflation, the universe continued to expand, but at a much slower rate. The observable universe. What we can see. The expansion of the universe also affects how far we can observe. The observable universe is the region of the universe that we can see with our telescopes, limited by the speed of light and the time since the Big Bang. The furthest we can see is about 13.8 billion light-years away, which corresponds to the current age of the universe. This doesn't mean the universe is only 13.8 billion years old, but rather that we can only observe objects that are within this distance. Beyond this distance, light has not had enough time to reach us since the Big Bang. However, the expansion of space means that objects beyond this observable region are actually much farther away than their light travel time suggests. The light horizon is constantly shifting as space continues to expand, and in the future, we will lose the ability to observe distant galaxies as they move farther away. The ultimate fate of the universe. A continuing expansion. As the universe expands, we must ask, how far will it go? The answer depends on the nature of dark energy and the overall density of the universe. If the effects of dark energy continue to dominate, the expansion will continue to accelerate indefinitely. In this scenario, galaxies will continue to move farther apart, and eventually, stars will burn out. The universe will grow increasingly dark and cold in a process known as the Big Freeze, where the universe continues to expand forever but becomes increasingly barren as stars exhaust their fuel. However, if dark energy's influence wanes or gravity overpowers it, the universe could slow down and eventually collapse in a big crunch where all galaxies, stars, and matter collapse back into a singularity. While current evidence suggests that the universe's expansion is accelerating, the ultimate fate of the universe is still a topic of active research. The search for a unified theory. Understanding the expansion of the universe and the forces that govern it remains one of the most exciting areas of scientific research. The discovery of dark energy and the observation of cosmic inflation have opened new doors in our understanding of the universe's origins and evolution. Yet, there is still much to learn about the fundamental forces at play. The search for a unified theory of everything, a theory that combines the forces of gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, continues. A unified theory could help scientists understand the nature of dark energy, dark matter, and the expansion of the universe in a way that brings together all the known laws of physics. The future of cosmic exploration. The future of cosmic exploration is full of promise. With advancements in telescope technology, like the James Webb Space Telescope, and new methods of studying cosmic phenomena, we are sure to learn more about the universe's expansion and its ultimate fate. As we continue to explore distant galaxies, exoplanets, and cosmic phenomena, we are sure to uncover even more mysteries that will shape our understanding of the cosmos. The universe's expansion is just one of the many cosmic stories that remain to be written, and each new discovery takes us one step closer to understanding the forces that govern everything we see. As the universe expanded and cooled after the Big Bang, it began to take shape in increasingly complex ways. From the first simple atoms of hydrogen and helium to the formation of the stars, galaxies, and larger cosmic structures, the universe underwent a series of transformations that would set the stage for the creation of everything we know today. The formation and evolution of these cosmic structures were critical to the development of the universe as we experience it. In this chapter, we'll explore how the universe's large-scale structures, galaxies, galaxy clusters, superclusters, and the cosmic web, formed, evolved, and continue to influence the cosmos today. The formation of the first galaxies. After the Big Bang, The universe was filled with gas, mostly hydrogen and helium, but no stars or galaxies. However, as the universe continued to expand and cool, gravity began to work its magic. Gravitational attraction started to pull matter together into denser regions, which would eventually lead to the formation of the first stars and galaxies. The earliest galaxies were likely small and irregular in shape, made up of the first generations of stars. These early galaxies formed from the hydrogen and helium that filled the universe. They were often referred to as population 3 galaxies. These galaxies contained only the simplest elements, as heavier elements had not yet formed. The stars within these galaxies were massive and short-lived, burning through their fuel quickly. Over time, these early galaxies merged, grew, and evolved, eventually forming the larger, more structured galaxies we see today. The gravitational pull of these galaxies helped to organize the surrounding gas and dust, and through countless cycles of star formation, they began to acquire the familiar shapes we recognize, such as spiral and elliptical galaxies. The role of dark matter in the formation of structures. While visible matter like gas and stars played a role in the formation of galaxies, the role of dark matter was equally important. Dark matter, which makes up about 27% of the universe's total mass, does not emit light and cannot be directly observed. However, its presence is inferred from its gravitational effects on visible matter. Dark matter played a critical role in the formation of galaxies by acting as a scaffold or cosmic glue that helped pull gas clouds together, allowing them to form the first stars and galaxies. Dark matter is believed to form dark matter halos around galaxies, providing the necessary gravitational pull to keep galaxies from flying apart due to their rapid rotation. These halos of dark matter also help to shape the large-scale structure of the universe, creating regions of higher density where galaxies could form and cluster together. Galaxy clusters, the next level of structure. As galaxies formed and evolved, they didn't remain isolated. Galaxy clusters, which are large collections of galaxies bound together by gravity, began to form. These clusters contain hundreds or even thousands of galaxies, and they represent one of the largest structures in the universe. The largest galaxy clusters are known as superclusters. These superclusters contain multiple galaxy clusters, making them some of the largest known structures in the universe. Superclusters are interconnected by vast voids of space, creating a complex cosmic web that spans the entire observable universe. This large-scale structure, often referred to as the cosmic web, consists of filaments of galaxies and galaxy clusters connected by vast cosmic voids. The cosmic web, a network of structures. The cosmic web is one of the most remarkable aspects of the universe's large-scale structure. The universe is not randomly distributed with galaxies scattered evenly across space. Instead, galaxies are organized into a vast network of filaments, long, thread-like structures of galaxies and galaxy clusters that stretch across billions of light years. These filaments connect to form a web-like pattern with voids in between where few galaxies exist. The cosmic web is shaped by the gravitational forces of dark matter, which form the foundation of these filaments. Over time, gravity has drawn galaxies and galaxy clusters together, forming the cosmic web's intricate structure. The galaxies in the filaments of the web are connected by vast stretches of dark matter, while the regions between the filaments, the voids, remain largely empty. The discovery of the cosmic web has revolutionized our understanding of how galaxies and large-scale structures are distributed throughout the universe. It has also provided valuable insight into the role that dark matter plays in shaping the universe's overall structure. The evolution of large-scale structures. The evolution of large-scale structures in the universe is an ongoing process. Galaxies continue to form, collide, and merge, shaping the structure of the cosmic web over billions of years. The process of galaxy merging plays a significant role in the evolution of cosmic structures. When galaxies collide, their gas clouds compress, triggering new star formation. Eventually, these merged galaxies settle into a new, larger galaxy. While the universe's expansion continues to push galaxies farther apart, gravitational interactions continue to bring galaxies together. This means that although galaxies are moving apart due to the expansion of space, galaxies within clusters continue to interact and evolve, and new structures are constantly being formed. Over the next few billion years, it is predicted that the Milky Way will collide with the Andromeda Galaxy, the closest large galaxy. This collision will lead to the formation of a larger galaxy, possibly an elliptical galaxy, and the merging of the two galaxies will significantly alter the structure of the local cosmic web. The role of supermassive black holes. At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole. These black holes can have masses ranging from millions to billions of times that of the Sun, and they play a crucial role in the formation and evolution of galaxies. Supermassive black holes are thought to have formed early in the history of the universe and grew over time by accreting gas, dust, and even entire stars. These black holes are not just gravitational sinks, they also have a profound effect on their surrounding galaxies. The energy released by matter falling into these black holes can influence the rate of star formation in the galaxy, creating a feedback loop that regulates the galaxy's growth. In some cases, supermassive black holes power the active galactic nuclei, AGN, which are extremely bright regions at the centers of galaxies. These regions emit vast amounts of energy as matter is consumed by the black hole, often outshining the entire galaxy. The presence of AGN is one of the key signatures of an active galaxy. The continued evolution of the universe. As the universe continues to expand, the cosmic structures we see today, galaxies, galaxy clusters, and superclusters, will continue to evolve. Some galaxies will continue to grow through mergers, while others may eventually run out of the gas needed to form new stars, causing them to fade away. The future of these large-scale structures is uncertain, but one thing is clear: the universe is not static. It is constantly changing, and the cosmic web continues to evolve. The future of galaxies, black holes, and large cosmic structures will be shaped by forces like gravity, dark matter, and dark energy, ensuring that the story of the universe is far from over. The role of observational technology. Our understanding of the evolution of cosmic structures has been greatly enhanced by modern observational technology. Telescopes like the Hubble Space Telescope, James Webb Space Telescope, and Chandra X-ray Observatory have provided us with detailed images of distant galaxies, galaxy clusters, and the cosmic web. These observations allow scientists to study the large-scale structure of the universe and track the evolution of galaxies over billions of years. As new telescopes and technologies continue to be developed, we will be able to probe deeper into the cosmos and learn more about the evolution of galaxies and the larger cosmic structures that shape our universe. One of the most intriguing questions in cosmology is, what is the ultimate fate of the universe? After the Big Bang, the universe has continued to expand, driven by forces like dark energy and gravity. But how will this expansion continue? Will it go on forever, or will the universe collapse back in on itself? The fate of the universe depends on a number of factors, including the nature of dark energy, the amount of matter in the universe, and how the forces of gravity and expansion interact over time. In this chapter, we'll explore the possible scenarios for the future of the universe, from continued expansion to a potential cosmic collapse, and how modern cosmology has shaped our understanding of the universe's end. The expanding universe, continuing forever. One of the most widely accepted theories for the future of the universe is that the expansion will continue indefinitely. The accelerating expansion of the universe, driven by dark energy, is one of the most significant discoveries in modern cosmology. Dark energy is believed to make up about 68% of the total energy content of the universe, and its repulsive force is pushing galaxies farther apart, accelerating the expansion of space. If dark energy continues to dominate the dynamics of the universe, it will drive the cosmos to keep expanding at an ever-increasing rate. In this scenario, galaxies will continue to drift away from each other, and the universe will become more and more diffuse over time. Stars will burn out, and galaxies will become isolated from one another, leading to a universe that is cold, dark, and empty. This future scenario is known as the Big Freeze, where the universe continues to expand forever, eventually reaching a state of maximum entropy. In this far-off future, stars will have exhausted their fuel, and the universe will be left with faint remnants of its former glory: dead stars, black holes, and cold, dark matter. The Big Freeze. A universe frozen in time. The Big Freeze is the scenario most scientists currently believe is the most likely. In this outcome, as the universe expands, stars will continue to burn out, and galaxies will continue to drift away from one another. Over trillions of years, new star formation will cease, and the remaining stars will eventually burn through all their fuel, leaving only white dwarfs, neutron stars, and black holes behind. As the universe continues to expand and cool, the temperature will drop to near absolute zero, making it impossible for life to survive. In this cold, dark universe, there will be little activity. The once vibrant cosmos will become a quiet, lifeless expanse of empty space. This scenario could take billions to trillions of years to unfold. Stars and galaxies will continue to fade and disappear, leaving behind a universe that no longer has the conditions for life to exist. The Big Freeze represents a slow, inevitable end to the universe, a gradual decline into darkness. The Big Crunch. The possibility of a cosmic collapse. The Big Crunch is an alternative theory about the fate of the universe. It suggests that instead of continuing to expand forever, the expansion of the universe will eventually slow down and reverse. If the amount of matter in the universe is high enough, the gravitational pull of that matter could eventually overcome the effects of dark energy, causing the universe to collapse back in on itself. In this scenario, galaxies, stars, and planets would be drawn toward a single point. The universe would contract, with galaxies colliding and merging as everything is pulled toward the center. Ultimately, all matter would be compressed into a singularity, an infinitely dense point, where the laws of physics as we know them would break down. This would mark the end of the universe as we understand it. The Big Crunch is a dramatic scenario, and it depends on the total amount of matter in the universe. If there is enough matter to slow the expansion, gravity could eventually reverse the universe's expansion. However, current observations suggest that the universe's expansion is accelerating due to dark energy, making the Big Crunch seem less likely. The Big Rip, a violent end. Another speculative possibility for the fate of the universe is the Big Rip. In this scenario, dark energy grows stronger over time, causing the expansion of the universe to accelerate at an increasingly rapid pace. Eventually, the force of dark energy becomes so strong that it overcomes all other forces, including gravity and the forces that hold galaxies, stars, planets, and even atoms together. In the Big Rip scenario, galaxies would first be torn apart, followed by the destruction of stars, planets, and other objects. Eventually, even atoms themselves would be pulled apart, and the universe would end in a cataclysmic event where everything is shredded into its fundamental components. The Big Rip is a more extreme and dramatic fate for the universe, and its likelihood depends on the properties of dark energy. If dark energy's repulsive force continues to grow stronger, this scenario could become a reality in the distant future. However, the specifics of dark energy are still not fully understood, and scientists are unsure whether this scenario is likely to happen. The role of black holes in the universe's fate. Black holes, the mysterious and incredibly dense remnants of massive stars, may also play a significant role in the fate of the universe. In the far future, as stars burn out and galaxies drift apart, black holes will become some of the only remaining active objects in the universe. Over time, black holes will slowly lose mass through a process known as Hawking radiation, named after physicist Stephen Hawking. According to this theory, black holes emit radiation due to quantum effects near their event horizons. This radiation causes black holes to lose mass gradually, and eventually they may evaporate completely. However, the process of black hole evaporation takes an incredibly long time. For example, a black hole with the mass of the Sun would take longer than the current age of the universe to evaporate. In the far future, black holes will be among the last remnants of the universe, and their slow evaporation could mark the end of all matter in the cosmos. The heat death. A universe at maximum entropy. Another possible outcome for the universe is the heat death, which is related to the Big Freeze scenario. Over time, as the universe expands, it will approach a state of maximum entropy, a condition in which all matter and energy are evenly distributed across space, and no thermodynamic processes can occur. This would result in a universe where no stars shine, no planets exist, and no life can survive. In the heat death scenario, the universe would be in a state of thermodynamic equilibrium, with no usable energy remaining. Everything would be uniformly spread out, with no way for matter to interact or form new structures. This outcome represents the ultimate end of the universe, where it reaches a state of perfect cosmic stillness. The future of cosmic exploration. Even though the fate of the universe may be determined by forces like dark energy, gravity, and the evolution of black holes, humanity's search for answers continues. Cosmic exploration is still in its infancy, and our understanding of the universe is constantly evolving. Advances in technology, such as the James Webb Space Telescope, the Large Hadron Collider, and other observatories, continue to expand our knowledge of the cosmos and its ultimate fate. In the future, we may uncover new phenomena that challenge our current theories of the universe's end, whether through the study of dark energy, the observation of distant galaxies, or the exploration of black holes. Humanity's journey into understanding the universe is far from over. Our cosmic adventure is just beginning, and it will take us to the very edges of space and time. Conclusion: the universe's uncertain future. The future of the universe is uncertain, shaped by the interplay of dark energy, gravity, and the expansion of space. Whether the universe will continue to expand forever, collapse in on itself, or meet some other dramatic fate remains a mystery. However, one thing is certain: the universe will continue to evolve, and our understanding of its future will deepen as we explore its many mysteries. The fate of the universe, while far from fully understood, is one of the most exciting questions in cosmology. As we continue to study the cosmos, we are bound to uncover new insights that will reveal more about the forces shaping our universe's past, present, and future. One of the most profound questions humanity has ever asked is, are we alone in the universe? Given the vastness of space, it seems almost impossible that Earth is the only planet to host life. From the search for microbial life on Mars to the hunt for alien civilizations in distant star systems, the search for extraterrestrial life has captivated humanity for centuries. But how do we go about answering this age-old question? And what do recent discoveries tell us about the potential for life beyond Earth? In this chapter, we'll explore the ongoing quest to find extraterrestrial life, the science behind these searches, and the implications for our understanding of life in the universe. The Drake equation, estimating the odds of alien life. One of the first serious attempts to estimate the likelihood of finding extraterrestrial life came in 1961, when Frank Drake, an American astronomer, formulated the Drake equation. The equation was designed to calculate the number of active communicative extraterrestrial civilizations in the Milky Way galaxy, based on several factors such as the rate of star formation in the galaxy, the fraction of stars that have planets, the number of planets that could potentially support life, the likelihood that life develops on those planets, the lifespan of technological civilizations. While the Drake equation has many uncertainties, some factors are still unknown or hard to measure, it was a groundbreaking step in thinking about the probability of alien civilizations existing. Even if we can't solve the equation perfectly, it gives us a framework for understanding the scale of the search for extraterrestrial life. The most important insight from the Drake equation is that the universe is vast, and with billions of stars and potentially habitable planets in our galaxy alone, the possibility of life existing elsewhere is significant. However, the equation also highlights just how little we know about some of the key variables, like how often life actually develops, or whether intelligent civilizations can survive for long periods. The search for life in our solar system. While the search for extraterrestrial life extends far beyond our solar system, there are several places within our own solar system where conditions might support life, or at least once may have. 1. Mars. The red planet. Mars has long been a focal point for the search for extraterrestrial life. As the fourth planet from the Sun, it is one of the most Earth-like planets in terms of surface conditions. Scientists have discovered evidence of ancient river valleys, lake beds, and polar ice caps, suggesting that Mars may have had liquid water on its surface in the past. The discovery of organic molecules on Mars by the Curiosity rover has raised hopes that microbial life could have once existed on the planet. While there is no direct evidence of life on Mars, scientists continue to study the planet in the hope of finding signs of past or present life, particularly in underground ice or in the planet's ancient lake beds. The Perseverance rover, which landed on Mars in 2021, is collecting samples to be returned to Earth in the future for analysis. This mission aims to search for signs of ancient life in the Jezero crater, an area that once contained a lake. 2. Europa, a moon of Jupiter. Europa, one of Jupiter's moons, has long been considered one of the most promising places to search for life beyond Earth. Europa is covered by a thick layer of ice, beneath which there is likely a subsurface ocean of liquid water. The ocean may be in contact with a rocky seafloor, providing the potential for hydrothermal activity, a key ingredient for life as we know it. In 2024, NASA's Europa Clipper mission is set to launch to explore Europa in greater detail. This mission will investigate the moon's ice shell, ocean, and potential for habitability. If life ever existed, or currently exists on Europa, it would likely be microbial. But the discovery of life on a moon of Jupiter would have profound implications for our understanding of life in the universe. 3. Enceladus, a moon of Saturn. Another candidate for extraterrestrial life in our solar system is Enceladus, a moon of Saturn. Enceladus is similar to Europa in that it has an icy surface and an underlying subsurface ocean. However, what makes Enceladus especially intriguing is the discovery of water geysers erupting from its south pole, which contain organic compounds such as methane and carbon dioxide. The presence of these compounds suggests that Enceladus could have the necessary ingredients for life, and scientists are eager to study the geyser samples further. The Cassini spacecraft, which explored Saturn and its moons for over 13 years, confirmed these findings, and future missions may investigate the moon's ocean in greater detail. The search for extraterrestrial intelligence, SETI. While searching for microbial life is exciting, the search for intelligent life is what often captures the imagination. The search for extraterrestrial intelligence, SETI, is an ongoing scientific effort to detect signals from extraterrestrial civilizations. SETI researchers use radio telescopes to listen for artificial signals such as radio waves or laser pulses that might be emitted by distant alien civilizations. One of the most famous moments in SETI history occurred in 1977, when a researcher named Jerry Emin discovered a mysterious radio signal coming from the constellation Sagittarius. The signal, now known as the WOW signal, lasted for 72 seconds and was never detected again. While it remains unexplained, the WOW signal has sparked continued interest in the search for extraterrestrial communications. Despite decades of searching, no definitive evidence of extraterrestrial intelligence has been found. However, advancements in technology, such as the development of more sensitive telescopes and the search for technosignatures, evidence of advanced technology, are giving scientists new tools to look for signs of alien civilizations. The role of exoplanets in the search for life. In the past few decades, the discovery of exoplanets, planets that orbit stars outside our solar system, has revolutionized the search for extraterrestrial life. Thanks to the efforts of telescopes like Kepler and TESS, we now know that planets are common in the galaxy, with billions of exoplanets potentially orbiting in the habitable zone of their stars, the region where conditions might be right for liquid water to exist. The discovery of Earth-like planets in the habitable zone has led to speculation about the possibility of alien life. For example, the discovery of the exoplanet Proxima b, orbiting the star Proxima Centauri, has raised hopes that life could exist on a planet just over 4 light-years away. Though we don't yet have the technology to visit these distant worlds, the growing number of discovered exoplanets means that there are many more opportunities to study potentially habitable worlds. In the coming years, missions like the James Webb Space Telescope will allow scientists to study the atmospheres of exoplanets in greater detail, looking for signs of biosignatures, chemical markers that could indicate the presence of life. The Fermi paradox: why haven't we found alien life? Despite the high probability that life exists elsewhere in the universe, we have yet to detect any definitive signs of extraterrestrial life. This paradox is known as the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the vast number of stars and planets in the galaxy, why haven't we detected any signals from alien civilizations? There are several possible explanations for this paradox. 1. Civilizations may be too far away. The universe is vast, and even the closest civilizations may be too far away for us to detect. 2. Technological limitations. Our ability to detect signals from other civilizations is still limited, and we may not yet have the technology to pick up their communications. 3. Civilizations may be short-lived. It's possible that technological civilizations have short lifespans, either due to self-destruction or other cosmic events, making it unlikely that we would detect them at the same time. 4. We are not looking in the right way. There may be forms of communication or technology we don't yet understand, meaning we could be missing alien signals or signs. The implications of discovering alien life. The discovery of extraterrestrial life, whether microbial or intelligent, would have profound implications for humanity. It would challenge our understanding of life's origins, our place in the cosmos, and our future as a species. For many, the search for alien life is not just about answering a scientific question, it is about connecting to the larger universe and understanding the deeper mysteries of existence. The discovery of alien life would also have philosophical and cultural implications. How would societies react to the knowledge that we are not alone? Would it change our views on religion, philosophy, and the nature of life? How might it affect our technological and social progress? As we continue our journey through the universe, we encounter two of the greatest and most profound mysteries in modern cosmology: dark matter and dark energy. These elusive substances make up approximately 95% of the total mass and energy content of the universe, yet we cannot see or directly detect them. Despite their invisible nature, dark matter and dark energy have a profound impact on the structure, evolution, and future of the universe. In this chapter, we will explore the nature of dark matter and dark energy, how they were discovered, their effects on the universe, and the questions that still remain unanswered. The mystery of dark matter. First proposed in the 1930s by Swiss astronomer Fritz Zwicky, dark matter was identified due to its gravitational effects on visible matter. Zwicky noticed that galaxies in clusters were moving much faster than expected given the amount of visible matter present. If only the visible matter, stars, gas, and dust, were contributing to the galaxy's gravitational pull, the galaxies should have been flying apart. The fact that they were staying together suggested that there was some invisible matter providing additional gravitational force. This invisible matter was eventually dubbed dark matter. Though dark matter doesn't emit, absorb, or reflect light, hence its name, scientists have inferred its presence based on its gravitational influence on visible objects in space. It doesn't interact with electromagnetic radiation, such as light, but it does interact gravitationally, influencing the motion of galaxies and galaxy clusters. The role of dark matter in the formation of galaxies. Dark matter plays a crucial role in shaping the structure of the universe. In the early universe, after the Big Bang, The universe was filled with hydrogen and helium. These elements were pulled together by the force of gravity to form stars and galaxies. However, without dark matter, galaxies wouldn't have been able to form as quickly or in the way we observe them today. Dark matter acts as a scaffolding for galaxies, providing the necessary gravitational pull to hold them together despite their rapid rotation. Without dark matter, galaxies would have flown apart because the visible matter alone wouldn't have been enough to keep them intact. The dark matter halo, a vast invisible region of dark matter surrounding galaxies, plays a critical role in this process. Recent observations using advanced telescopes have shown that dark matter is present in the halo of galaxies, surrounding them like a cosmic cocoon. This halo of dark matter helps galaxies form and remain intact over billions of years, while simultaneously influencing the motion of stars and gas within the galaxy. The discovery of dark energy. While dark matter was identified as a gravitational anomaly, the discovery of dark energy came much later. In the late 1990s, astronomers studying distant supernovae, exploding stars, made an unexpected discovery. They found that the expansion of the universe was accelerating rather than slowing down as they had originally expected. This was a profound revelation, as the prevailing thought at the time was that the force of gravity should slow down the universe's expansion over time. However, the observations revealed that some mysterious force, now called dark energy, was counteracting gravity and driving the universe apart at an accelerating rate. Dark energy is believed to make up about 68% of the total energy content of the universe, yet it remains largely undetected. Unlike dark matter, dark energy doesn't exert a gravitational pull on objects. Instead, it is a force that seems to push galaxies apart and accelerate the expansion of the universe. Dark energy is thought to be uniformly distributed throughout space, and its effects are visible on cosmic scales, pushing galaxies farther apart. The effects of dark matter and dark energy on the universe. Together, dark matter and dark energy shape the structure and fate of the universe. Dark matter acts as the glue that holds galaxies and galaxy clusters together, providing the necessary mass for the formation of large-scale cosmic structures. Without dark matter, galaxies would not have been able to form as quickly or remain stable over time. Meanwhile, dark energy is responsible for the accelerating expansion of the universe, pushing galaxies away from each other at an ever-increasing rate. It's as if the universe is stretching out, and dark energy is the force causing this expansion to speed up. The effects of dark energy are visible on the largest scales of the cosmos, influencing the distribution of galaxies and the future of the universe. What is dark matter made of? Although we know dark matter exists, we still don't know exactly what it's made of. Scientists have proposed several possibilities for the composition of dark matter, with the two leading candidates being WIMPs, weakly interacting massive particles, and axions. 1. WIMPs. WIMPs are hypothetical particles that interact with regular matter through the weak nuclear force and gravity, but not through electromagnetism, meaning they don't emit light. These particles could be massive, which is why they exert such a strong gravitational pull. WIMPs are currently one of the most studied candidates for dark matter, and experiments are being conducted to detect them directly. 2. Axions. Axions are another theoretical type of particle that could make up dark matter. These particles are incredibly light and interact with matter very weakly, making them difficult to detect. If axions exist, they could provide the missing mass in galaxies and explain the behavior of dark matter. The fate of dark matter and dark energy. Although we don't know what dark matter is made of, we do know that it has been around since the early universe. It played a key role in the formation of galaxies and continues to influence the motion of galaxies today. Over the next several billion years, dark matter will continue to shape the growth and evolution of cosmic structures. Dark energy, on the other hand, will likely play a role in determining the ultimate fate of the universe. If dark energy continues to dominate, the universe will continue to expand at an ever-accelerating rate. This could lead to the Big Freeze, where galaxies move farther and farther apart and stars burn out, leaving the universe a cold and dark place. The search for dark matter and dark energy. Despite their profound influence on the universe, dark matter and dark energy remain largely mysterious. Scientists are actively searching for more information about both. Experiments like those at the Large Hadron Collider are looking for evidence of dark matter particles like WIMPs, and future space-based missions, such as the James Webb Space Telescope, will help scientists study the effects of dark energy on cosmic scales. By better understanding dark matter and dark energy, scientists hope to uncover the fundamental forces that govern the universe and its future. These two invisible forces remain among the most exciting areas of research in cosmology, and new discoveries could revolutionize our understanding of the cosmos.